Okay, we're going to be doing trig graphs. If you go to my website, you will be able to find the blank sheets that go with this so you can fill in as you follow the lesson with me. We're going to run through a few graphs. We're going to be doing the trig graphs. You probably saw these last year. But again, we're going to go through this as if you haven't seen it before so that we can fill in any gaps if you're missing them. So again, go to my website, go to the MHF 4U course, and it will be under the Unit 5 folder. Okay, most people remember our sine graph, and they probably remember the shape. I'm sure you've discussed this in the last unit with your teacher. And again, most people remember it started at the origin, it kind of went up and went down and came back up again. So we're going to do it a little more formally, like we did last year, and this year we're going to be doing it over in radians between 0 and 2 pi. And this year we're very specific that we want to spread this over 12 squares. And the reason we want to spread it over 12 squares is because it'll make future transformations and translations easier. And as well, we want our vertical scale. We have quite a bit here that we can do. So we're going to fill that space. We're going to make 1, 2, 3, 4 squares is going to equal 1 unit. So we can fill up this space. So just to help out, I went and did a table of values on Desmos. So if you look, you can see right here, that is our table of values from Desmos. And I'm going to go and plot those. So again, we're going to spread this sine curve over 12 squares. So I'm going to go and plot those points, and then I'm going to explain how we get them so quickly. So let's plot them. So if we spread this over 2 pi, being 1 full revolution, and we'll go and label that right here, you can almost see that the sine curve is cut into quarters. So if you look, when we draw it, we have our first quarter that goes up to 1, our second quarter that makes the half of the sine curve, comes back down to 0. We go down to -1, that's another quarter, and then back up to the starting point, or where we're going to start to repeat. So if we look, that would be over 12 squares, and each quarter would be 1, 2, 3 squares, another 3 squares, another 3 squares, and another 3 squares, because 12, if you cut it into quarters, is 3 squares. Now the problem is, a lot of students give us the zigzag curve. So if we take a look, don't do this on your sheet right now, but we'll get this nice little zigzag curve, and that is not a sine curve. Sine curve has curves in it. So how do we get it so that we don't get the zigzag curve? So let's undo this, and let's go back and look at the table of values for a sec. So if we look, we have some other really nice points here. So we have this point here, which is at pi over 6. You guys like to think that is 30 degrees. And we have another one here at 5 pi over 6. That's a really nice point right there. And you guys like to think of that as 150 degrees. See all these other really, really nice ones. So they're actually not so hard to plot. So let's go back to the graph. And if you go and plot those, let's think about our scale first so that we can figure out where those are located. So our scale, if this right here was 2 pi, then this would have to be, hopefully you're thinking pi. So let's label that. And if this is pi, then this right here would have to be cut in half again. So that would be cut in half again to give me pi over 2. And then for the last piece, there's a few ways you can think of this. You can think if you were working in degrees, this is 0 right here. And then right here would be 90 degrees, 180. This would have to be 270. And some people just know that 270 is 3 pi over 2, or they'd have to convert that to get it. The way I think of it is this takes 3 squares to get to pi over 2. So if I wanted to get all the way over to here, I'd have to do that once, twice, 3 times. So that means I just have to triple this to give me 3 pi over 2. Now if I go and figure out what each square is pi over 6. How did I get that so quickly? Well, if you look, this is pi over 2, and that takes 1, 2, 3 squares to get. So pi over 2 divided by 3, that will give me pi over 6. Or, if you like thinking in degrees better, this is 90 degrees, so that would have to be 30 degrees right here. And we remember that that's pi over 6. Now, I don't like labeling that as pi over 6 because I'm going to get way too much on my scale here that's going to cramp it up. So I only label the 1, 2, 3, 4 radians there. But I know that the other ones are there, and now I can go and plot the pi over 6 at a half. Because remember, we're sitting with this being 1 and this being -1. And if you go and look, here's another one at 5 pi over 6, sitting right here in my table of values. Okay, and that's going to be about 150 degrees. It's going to sit right in there. I'm going to go and plot it. And I'm going to get these points here. So if I take a look at those, that makes it so that my sine curve will look very nice and smooth and have the curves and not the zigzags. Now to remember these, everyone's really good, usually, to remember I'll call them primary points, the max, the mins, and where they hit the zeros. Okay, and I call these the halfway points. I think Miss St. Hilaire might call it the shoulder points. So if I take a look here, the way you remember the halfway points is they're always from wherever your 0 is, and you just go over 1 and up halfway to whatever your max is. And again, so if you look, we have a 0 right here, over 1 and up halfway. Right here, I go over 1, and now this one's going to be down halfway towards that minimum here. And I have another 0 here, and I go over 1, and it's going to be down halfway to what my minimum was. And if I were to keep on going, because remember sine curves repeat, I would go over 1 and there'd be another point right here, up halfway to my maximum of 1. Now this is all ready for us to do a nice smooth curve through. We've graphed it on the interval they've required, so that's 0 to 2 pi. We started at 0 all the way to 2 pi. I've labeled my axes, or I've labeled them for you as well. So I'm all set to do a nice smooth curve. So do your best. The first few are difficult. I'm not sure how it's going to go on the iPad either. So do your best to do a nice smooth curve, and hopefully it turns out all right. That's about as good as I can get. We'll put arrows on the end. And remember, this is all contingent on doing it over 12 squares. So if you look, 12 squares this way to get me my 2 pi for it to repeat. And because we did it over 12 squares, that's why these nice halfway points work so well. You can't do that if you had done it over 8 squares or if you had done it over 6 squares. So that's why we specify 12 squares, because you can get those halfway points really easily. So if you take a look over here, we have to fill in this information. Some of it's pretty quick. My maximum is 1. My minimum is 1. My period, which is how often it repeats every 2 pi for a full cycle. My y-intercept is sitting right here where it crosses the y-axis, so that's going to be 0. My x-intercepts actually keep on going on forever. If you take a look, I have 0, I have pi, I have 2 pi, there'd be another one at 3 pi. They keep on going forever, but we're just going to list the ones for what we see on this graph for the intervals. So that's going to be 0, pi, and 2 pi. And then the domain, we're going to do the domain for the entire curve, not just the interval that was stated. So the domain, this curve would keep on going like this forever in this direction and ever in this direction. So my domain is just x is an element of real. X is an element of the real number system. And then my range, well, if you look, I always try and have my students say it in just plain English first. What can my y values be? Well, they can be anything between -1 and 1. So I have to specify that. doing it in math language. So I get y is an element of real such that we're between -1 and 1. And don't forget, I need that equality there. It could also equal -1 and 1. And that's the sine curve completely done. So I've done this in significant detail. I probably won't do the cos curve in as much detail, similarly, but I'll be a little quicker because they're so similar in the explanation. Just before I go to the next slide, I noticed that I used x in my domain, and I should have used theta. So if we take a look at this one, I've done the table of values here again. Again, the cos curve repeats over 2 pi. And we're going to go through and plot all of these points. We're still going to do it over 12 squares. So 2 pi is going to take up 12 squares on our horizontal axes. And then we're going to go and plot everything. So this one's going to be a little quicker. Let's zoom in a little. So if we take a look here, again, I'm going to be fairly quick, and you're going to have to memorize all these curves and how quick, and be very quick on when you graph them. So again, cos curve starts at the top, up at 1. So hopefully you remember the general shape. We usually start high, we zigzag and come back up. So again, following that with the 12 squares, we're going to get 1, 2, 3, all the way up at 4 squares up here, and then down here. Again, that was pretty quick. And then I'm going to go and do my halfway points. So my halfway points, wherever I'm at my 0, I go over 1 square and up halfway to my max. Here I'm going to go over 1 square and down halfway to my min. Here I'm going to go over 1 and down halfway towards my min. And here I'm going to go over 1 and up halfway to my max. So if we put those in nice and quick. And sometimes it's good to do a double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's over 12 squares. And remember, you could still get a zigzag graph here, which we don't want. And it's because those start, I don't want those very pointy here. Okay, so undo that. And you're going to do a nice smooth curve. And the idea when you're doing this is you want that nice round peaks at the top for the maximum and the minimum, because they're going to turn and come back down and turn and come back down. Okay, so let's try our best to do a nice smooth curve. And then we're going to put our arrows on the end and our scale. So our scale, remember, we span the whole horizontal axis. Takes 2 pi to repeat. Halfway here would be pi, halfway here would be pi over 2, and triple that, 3 pi over 2. At the end of every graph, you should always say, what would my teacher take marks off for? So if I take a look here, I'm missing my vertical scale. I go up to 1 and down to -1. And then we have all the information to specify right here, just like we did on the last one. So again, we go up to 1. For a max, -1 for a min, a period of 2 pi. My y-intercept, I'm now crossing right here at the y-intercept being 1. My zeros that I can see here are pi over 2 right here and 3 pi over 2. So we'll go and put those down. My domain, very similar to the sine curve. X is an element of real. And same for my range, like my sine curve, which was y is an element of real, such that y is always between -1 and 1, and could be equal to it as well. If we take a look, that's it. Now when you go and graph these, it should be just that quick. Dot, 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 and then go and do your halfway points. Again, you always know that you're going to span these over 12 squares, and then your max is going to be, if you have the space, you're going to go up 4 and then down 4. If you don't have the space, you can shrink that. I would shrink it to a nice number like 2, so you can still do nice halfway points, but we'll deal with that once you have these memorized. Again, I made the same mistake as earlier. I used x in my domain, and I should have used theta. So make sure you fix that on yours. So now we're going to take a look at tan. Again, just like last year, I went and notice our scale has, or our interval has changed. We're going from negative pi over 2 to 3 pi over 2. That's to incorporate full cycles. So again, we're going to use the same scale again. We're going to do 12 squares would be 2 pi. We just got to make sure that we go into the negatives a little. So let's zoom in. And let's take a look at this. We're going to start with the undefined spots are where my asymptotes would be. Okay, so again, a dotted line for my asymptote. So let's put our scale on here first, just because it's a little different interval. So I'm going to end up getting my 2 pi. So my pi over 2 is usually here, which would be my pi here. And then my 3 pi over 2 here. And that's as far as I have to go on the horizontal. And again, that will now be 9 squares. 3, 1, 2, 3, 1, 2, 3. And I have to go into the negative. So I'm going to get my negative pi over 2 right here. Okay. And now I'm going to go and draw my asymptotes right away. So I got to figure out how to do that on this. So give me a sec. Unfortunately, I couldn't find a dotted line tool, so I did my best. You have to use a ruler. You'll lose marks if you don't. And again, we're going to go and now put on a vertical scale. So if you look, and in my table of values, I have 1, but I know, and negative 1, but I know that because there's vertical asymptotes, I know the curve's going to approach it. So I don't want to put my 1 and negative 1 way up here, or it'll look way too stretched out. So you can either do a 1 right here, or you can do 1 right here, but much more than that, and it will make your graph look a little odd. So let's go and put that on there. So let's do 1 and 2 and 3 and negative 1 and negative 2 and negative 3. So we're going to go and plot this one right here. So if you look at negative pi over 4, which would be negative 45 degrees, if we were working in degrees, is at negative 1. So if I take a look, I know that this is negative pi over 2, so negative pi over 4 would have to be halfway, or if you're still kind of converting in your head, negative 90 degrees, that would make this negative 45 degrees, and we go and put our point. We end up getting one there, 0, 0, and there. And then it just repeats. And do your best to do a nice smooth curve through here. Now the one thing you have to remember, and I'm going to do this wrong first so that you don't make that mistake, is this is not our cubic function. So it should not have that full plateau. I exaggerated it a little. We shouldn't have a full plateau there. We should more cut through the horizontal axes. So it should really kind of go on a diagonal there. So let's go and do your best to draw it. I'll do it first. You'll see what it looks like, and then you'll try and copy it. So again, you'll see that we're approaching the asymptote here and here. It's going to go all the way up to positive infinity and down to negative infinity here, and it repeats twice on that interval of 2 pi. So really my period for this is going to be pi. So let's fill that in first. My max value does not exist because it goes up to positive infinity. My minimum value doesn't exist because it goes down to negative infinity. My y-intercept is 0. My x-intercepts that you can see here are 0 and pi. And here's where the next piece gets tricky. Let's do the range first because it's easier before we do the domain. So my range would be y is an element of real, or the real number system, and that's because it goes up forever and down forever, so I'll hit every y value there. Now I have to talk about the domain, and you'll see that right here it doesn't exist, right here it doesn't exist, right here it doesn't exist. That's going to continue forever and ever and ever as we go in both directions. So I can't just list them all because I'll be here forever. So I have to figure out a mathematical way to do it. So I'm actually going to do it a little lower here so I have space. So let's just go down here. I'm going to get x, I guess it should be theta. So let's switch that. Is an element of the real number system such that, and now I have to specify that it can't be equal to certain values. So it can't be equal to pi over 2. That's the first positive one. And if you look, there we go, can't equal the pi over 2. And if you notice, it's every pi that it repeats, even if I go backwards as well. So I have to say every multiple of pi from pi over 2. So the easiest way to say that is plus any multiple of pi where a is an element of the integers. So let's explain that a little more. So again, if you look, if I'm sitting here at pi over 2, if I let a equal 1, then I'm adding 1 full pi and I'd get to this one. If I let a equal 2, and I was starting at pi over 2, it would be plus 1 pi plus 2 pi, and I'd get the other asymptote that was over here. If you have trouble with that, we're going to come back to visit it again in class, and you can ask your teacher a little more. So by this point, you've got the routine of what has to happen. You have 3 more graphs to do. And for me to do this on the iPad would take me forever. It's already taken me forever to do the first half of this video. So if we take a look, I've given you the table of values, and you need to go through the same process with the same similar scale. So right now, you should pause the video, and you should go and try and fill in those other 3 graphs. Now, I'm going to go and skip to the final answer for these and discuss them with you. But again, you should be pausing it, trying to plot them yourselves. I know most of you are probably just going to be like, I'll go to the next page, see what it looks like, maybe fill it in. Definitely fill it in. And then you're going to have these all memorized. Just like in grade 11, when we gave you all those base curves, the absolute value, the quadratic, the cubic, the exponential, the reciprocal, all of those were memorized, and that's the same for this one. And if you don't, you're going to have significant difficulties when we go to graph this. So again, assume that you're going to have a quiz on this really soon, just asking you to do these base curves, and they should be memorized. So hopefully this is what your cosecant graph looked like. So you can see we have it almost looks like 2 parabolas, 2 U-shapes right here. And hopefully you got something very similar. Now I'm going to do some marking up on this graph just to kind of give you some strategies on how to relate this to the sine curve, because remember cosecant is just 1 over sine, and that will hopefully help you remember how to graph it. So don't mark up your graph. It should look just like this looks right now, but I'm going to put some marks on here and have a discussion to help you remember it. So again, if we look here, remember our sine curve, if we were to graph it right on here, we would have had these points here. And my halfway points would have been over 1, up halfway to my max. So if you look, this is 2 squares to get to my max for my sine curve. So I only went up 1 square here. And again, we get those. I'm going to do some rough work at the bottom. So if we take a look, remember the sine curve, y equals sine curve. Cosecant is just 1 over sine. It's the reciprocal. So again, I just have to flip it. So if I take a look here, if I were to take the sine value right here, that's y equals 0. Well, if I flip that and do, so sine at x equals 0 is 0, that means if this is 0, then this will be 1 over 0, okay? And that's why I pick up this vertical asymptote right here. Similarly here, okay? So I'm going to do one of these in detail. So if I take a look here, this is the one that confuses people the most. So if you look right there, if this is 90 degrees or pi over 2, then this would be 30 degrees or pi over 6. So if I was just doing my sine curve, I would go sine of pi over 6 equals 0.5 or 1 over 2. Okay, so that's why I got this point right here at a half. Now, that's not what I was dealing with. I was dealing with cosecant of pi over 6. And if you looked at the table of values, it gave me 2. But the reason it gave me 2 is this is 1 over sine of pi over 6, which would be 1 divided by 1/2, which would equal, I'm going to actually work down. And you'd have to invert and multiply, and that's how I get my 2. So again, whatever value you have on the sine curve, you just have to invert it when you're dealing with your y's. So again, if I look here, that was a half. When I flip it, I get 2. Right here is 1. When I flip it, I get 1. Right here is a half. When I flip it, it's going to go up to 2. When this is negative a half, I flip it, it goes down to negative 2. And that's how we get all of these points fairly quickly. And when you see me do it in class, you might even see me do these points really, really lightly just to get the shape. I'll probably do that just for explanation. I have it memorized now. And then at the very end, I quickly just go and I erase them because I don't need them. They're not part of my actual cosecant graph. Okay? And then we have to get our details off to the side. So if we take a look here, there's no maximum value because it goes up forever. There's no minimum value because it goes down forever. The period, again, it repeats every 2 pi. Since there's a vertical asymptote on my vertical axes, there's no y-intercept. There's no x-intercepts because it never crosses the x-axis. It should be the theta axes. And if we look here, I actually remembered when I did the notes today, theta is an element of real such that theta can never be a multiple of pi, where k is an integer. You can use a k. I think on the last one I used an a, just some value that isn't an x or a y that we don't use often in math. So right here, k pi. So if you take a look, this would be 1 pi, 2 pi, 3 pi's. Or if I wanted to go into the negatives, because it's for integers, I would have like negative 1 pi here onto the left side. You can't see it over there. So that means that I can't exist on any multiple of pi, and that's where I have my asymptotes. And if we look, my range, y is an element of real. I have y is always smaller than negative 1. That's this piece, smaller than negative 1. And then y is bigger than positive 1. And both of those have equality on it. So less than or equal to negative 1 and greater than or equal to 1. Okay? So go to the next one. The one thing you can't forget is to label your asymptotes. So theta equals pi and theta equals 2 pi. So again, if we look at this one, done very, very similar. So I'm going to just kind of skip to the shortcut discussion again. And again, don't mark up your curve. Your curve should look like this, and it looks great. So if we look here, my cos curve would be sitting in here. And again, my halfway points. Oops, missed that one. Right there. And again, I did all the reciprocals to get my points for my secant curve. So again, 1, flip it, it's still at 1. This is a half. So if I do, if I flip it, I'll be up at 2. 0, if I flip it, I'll get 1 over 0, and that's where I pick up my asymptote. So again, I'm going to erase those. Before I forget, I should label my asymptotes. So I get x, theta. Theta equals pi over 2. Theta equals 3 pi over 2. And then if I look at the details at the side, very similar. These do not exist. It repeats every 2 pi. I did pick up a y-intercept right here. There is no x-intercepts, or should be theta-intercepts. Domain, theta is an element of real such that theta cannot equal 2. So let me add that in there. Cannot equal 2. Pi over 2. And then adding any multiple of pi, because my asymptotes repeat every pi after that. And I get the same range. Okay, to start off, let's get our asymptotes on there. So let's do that first. So I got theta is equal to 0, and theta is equal to pi. Made a few mistakes over here on the information. So again, for this curve, just in general, I find this is probably one of the more difficult ones. I find it easier just to memorize where your asymptotes go and that the wave goes in the opposite direction as your tan curve. I find that the easiest. You can trust me. You saw the table of values. That's what it's going to look like. Let's go and look at our information. There's no max or min. The period is pi because it repeats every pi. There'd be another zigzag finished here and one up on this side, but I was graphing it for the interval that was specified. Most times in class, we'll ask you to graph one cycle, so you'll get just the nice piece that you see in the middle there. If we look at the x-intercepts, let's fill that one in. My x-intercepts are negative pi over 2, pi over 2, and 3 pi over 2. Again, my domain is for everything, so I'm going to do my domain down here where I have a little more space, domain. So I have theta is an element of the real number system such that we always start with our first asymptote. So if we look here, that's at 0, and then it's every multiple after that. So 1 pi, 2 pi, 3 pi. If I were starting at 0, I'd go back to negative 1 pi, negative 2 pi. So I have to specify what it can't equal. So that's going to be theta cannot equal any multiple of pi. And to make that just a multiple, k has to be integers. K is an element of the integers. Range, it goes up forever into positive infinity and down forever into negative infinity. So range y is an element of the real number system. Hopefully you understood this. Your teacher's going to follow up with you. The idea is you're going to have this done for tomorrow so that we can continue on. There is a few homework questions on the next slide, and you have to have this memorized. We cannot be starting transformations and having people not know how to do the sine curve quickly. So I'm going to emphasize that again with love, that these need to be memorized as soon as possible. And some questions here. So that's it. Hopefully it went all right. Sorry for the long video. Again, follow up with your teacher if you have issues, and have a good night.